Alright, lesson 2.4 is exponential function manipulation. And so for this lesson, our skills and learning objectives are going to use the properties of exponents and logarithms to simplify and evaluate expressions. We're going to apply the properties of logarithms to evaluate expressions and graph functions and understand their characteristics and effects of constants and the exponential model y equals a times b raised to the kx. Alright, so the properties of exponents are used to simplify exponential expressions. Let's recall those properties here and explore how they're related to graphs of exponential functions. And so if you remember when you learned about the properties of exponents, excuse me, when you have two things being multiplied or divided inside of a parenthesis, you can take the exponent on the outside and distribute it to both of them. I don't know why my marker's on, sorry about that. So it takes care of this one. So this gives us a to the m times b to the m. Same thing over here on the far right, bottom right one that they gave us. Because they're being divided, we can distribute that exponent, which will give us a to the n divided by b to the n. Alright, the next rule over on the top, the middle one, says if I have b to the m to the n, exponents are side by side. Remember, anything written side by side in math means to multiply. So we would just take the two exponents and multiply them. So b to the m raised to the n is the same as b to the m times n. Then we have our another rule that says when we're multiplying with like bases, we're going to keep the base and we add our exponents. So when we have b to the m times b to the n, they both have a base of b, so we keep the b and we add our exponents, so m plus n. Alright, I believe we talked about this one the other day. If we have b to the 1 divided by k, that's the same as a kth root of b. This is where I said if we have a root of some base raised to an exponent, then that's equal to the base raised to the exponent divided by the root. So same thing, the only thing here was the exponent was a 1, and so they had to the 1 right there. Then the middle on the bottom there is the negative exponent rule. I'm pretty sure we talked about that one. So if we have a negative exponent, we're going to send it to the bottom. Now we have a fraction. So that b to the negative n goes to the bottom. The n becomes positive. And we put a 1 on top to be a placeholder. Alright, then just some simple problems here in example 1. Says evaluate each number to 3 decimal places. So we're literally just going to type this in our calculators. So 5 raised to the 2.3. 3 raised to the square root of 7. And then 6 raised to the negative 1.5. Whoops. Yeah, sorry about that. Alright, then some characteristics of exponential functions of the form of f of x equals b to the x. So your domain is going to be all real numbers, and your range is consistent of the positive real numbers. Because remember, if it's b to the x, then you have a horizontal asymptote at y equals 0, and your graph is up above it. The graphs of all exponential functions of the form of f of x equals b to the x will pass through the point 0, 1, because f of 0 is equal to b raised to the 0 power, and anything to the 0 power equals 1. So your y-intercept is at 1. If b is greater than 1, then our function will be increasing, continuous, and it's concave up. If our b is between 0 and 1, our function is decreasing, continuous, and concave up. The graph of f of x equals b to the x approaches but does not cross the x-axis. Therefore, the x-axis, or y equals 0, is the horizontal asymptote. And then f of x equals b to the x is 1 to 1, and it has an inverse that is a function. Alright, so example 2 here says graph f of x equals 2 to the x and g of x equals 1/2 to the x on the same grid at the right. Then it wants to know what we can conclude about the relationships between those two graphs. Alright, so for y equals 2 to the x, I'm just going to pick me some x values here. There's no transformations going on, so I know I have a horizontal asymptote at y equals 0. So I plug this in. 2 squared, starting at the bottom here, is 4. 2 to the first is 2. 2 to the 0 is 1. 2 to the negative 1, remember negative exponent, send it to the bottom. So I got 2 to the first on bottom and a 1 on top, which is 1/2. And then 2 to the negative 2, again, send it to the bottom. So I have 2 squared on bottom, a 1 on top, which is 1/4. And so we can graph that one. So negative 2 and 1/4, negative 1 and 1/2, 0, 1, 1, 2, and 2, 4. We could have kept going. 3 would have gave us 8, and 4 would have gave us 16 if you want to continue it. Now, so when we look at y equals 1/2 raised to the x, we're not a big fan of fractions. So we can change this because 1/2 is the same as 2 to the negative 1. So if I'm going to bring that 2 back up, remember I have to change the sign of its exponent. It was 2 to the first on bottom, so now it's 2 to the negative 1 to the x, which is the same as 2 to the negative x. So when I do that, I can see that negative just makes it a reflection across the y-axis. So I'm just going to take each of these points that we just graphed and reflect them across the y-axis. So I'm going to take this first point that we graphed and go across the y-axis. The second point. Now, with 0, 1, if I go across the y-axis, it doesn't move. Okay, third point, our fourth point, the next point, and I'm even going to go up to the one that's up at 16. I'm going to go across the y-axis, and it's up there. All right, and so there is my 1/2 x. So label that here. So y equals 1/2 to the x. And this was y equals 2 to the x. And remember, there's also still, though, that horizontal asymptote at y equals 0. It didn't change. The only thing that's going to change it is if we shift our graph up or down. And then a reflection may affect it depending on the shift. Alright, so transformations of exponents. So we did this with regular functions. We had said like a quadratic and all of them. We said we had y equals a times like bx minus h squared plus k. We even looked at it with logarithms, I believe. Maybe not yet. Maybe it's coming. But we looked at it with like quadratics. We looked at it with absolute value. We looked at it with a bunch of the different parent functions, even rational functions. So the same thing with exponential. So we got y equals a times our base raised to the bx minus h and then a big plus k. Alright, it all does the same thing. K is still our vertical shift up or down. If it's positive, it goes up, negative goes down. H is still that horizontal shift left or right. Does the opposite of what we think it should. If it says x minus 3, we're going to go to the right 3. If it says x plus 6, we're going to go left 6. A is our vertical dilation, and we're going to kind of change from using stretch or compression. Actually, or letting us just get by with dilation, so I'm going to start trying to use that. Vertical dilation by whatever that number is. But just remember, if that number is greater than 1, it's a stretch, and if it's between 0 and 1, it's a compression or a shrink. They put the horizontal as AX inside there. That is just our B, okay? So this is, I'm going to change that to B there because that's what we've been consistent with. All right, if it's between 0 and 1, change that to B right there as well. So we do have between 0 and 1, that means it's going to stretch by that reciprocal, and if it's greater than 1, it's going to compress or shrink by the reciprocal as well. All right. And then we have the reflection. If the negative is out in front, it's across the x-axis, and if it's inside with x, it's a reflection across the y-axis. So nothing new except how it's going to look, but that's just because it's an exponential function. All right, so example 3. Once it's a graph, f of x equals 3 to the x on the grid at the right, then use the graph to obtain the graph of g of x equals 3 to the x plus 2. All right, so f of x equals 3 to the x. So I have 3 to the negative 2, which negative exponent will send it to the bottom, so it's 1 over 3 squared, which is 1 over 9. 3 to the negative 1, which is 1 over 3 to the positive 1, which is 1/3. 3 to the 0, anything raised to the 0 is 1. 3 to the first is 3, and 3 squared is 9. And so there's my ordered pairs. Also remember, this is just a parent function, so I have a horizontal asymptote, and it's at y equals 0. Then our g of x equals 3 to the x plus 2. So we know that x plus 2 just means that we're going to take our x's and we're actually going to subtract 2 because we're going to the left 2. So I'm just going to rewrite my ordered pairs here. So I'm going to take all my x's and subtract 2. And my y's will stay the same. And my horizontal asymptote is not affected by the x's at all because it's a y equal, so it's still going to be at y equals 0. Now, something else we can do, since we know that this is just going to make our graph go to the left 2, I could literally have gone up to my graph and taken each point and moved it to the left 2. And that's all I'm showing right here is I'm taking the point and then I'm moving it to the left 2. And you'll notice those are the exact same ordered pairs that we just got. Example 4 is to show that the transformation g of x equals 3 to the x plus 2 can be written in the form of h of x equals a times b to the x using the transformation properties in the table above. Describe the transformation of the y-intercept from the parent function f of x equals 3 to the x for g of x and h of x. Alright, so what we're going to do is we're going to start out with, we know that g of x is equal 3 to the x plus 2. Now remember what made us add the exponents. We added the exponents when we had like bases and they were being multiplied. So I could say this is the same thing as 3 to the x times 3 to the 2. Okay, that's one of those rules we saw at the very beginning. It's actually the third one in the top row. Okay, so it's the one on the far right, top row, under the properties of exponents. And then we know that 3 squared, we can work that out. So we get 3 to the x times 9. In multiplication, the order doesn't matter, so I'm going to switch these around. So this is the same as 9 times 3 to the x. And so now we are in the form of h of x, where my a is 9 and my b is 3. Oh, I don't know why I boxed that. Alright, then it says also to describe the transformations of the y-intercept from the parent function f of x equals 3 to the x for g of x and h of x. Alright, well, on g of x, our graph shifted to the left 2. So the y-intercept, which was 0, 1, is now negative 2, 1. And then for h of x, well, we know that that's in the form, that's a geometric sequence form. That's at a sub 0 times b to the x. So because of that, that was supposed to be an e. So a sub 0 is equal to 9, which means you had the ordered pair 0, 9 is the y-intercept. And that is the end of lesson 4A.